I grew up in Pakistan, and before Pakistan came into existence, of course, it was all India. And we lived in Karachi, which is a major city in Pakistan. And I went to high school there, and then did first 2 years of college in Karachi. And in 1952, I came to the United States to study engineering at the University of Michigan. And I started in an aeronautical engineering program. And after the first year, I thought, well, maybe this wouldn't be so useful for me. So I switched to mechanical engineering. And so I did mechanical engineering and graduated in 1955. And then I worked for a couple of years in Detroit as a mechanical engineer, about a year and a half. And I didn't really like what I was doing. I found it boring. And I was designing farm implements. So I had an opportunity to apply for and get a scholarship to study petroleum engineering. And the reason I got interested in petroleum engineering was that at about that time, Pakistan had discovered a large gas field. So I thought I'd go back and work there. And so I got a scholarship to go study petroleum engineering in Canada at the University of Alberta. I really liked petroleum engineering, and I found it more exciting, the problems more challenging. In fall of 59, I came back to Canada, to the University of Alberta, did a master's in petroleum engineering, and worked on research related to multi-phase flow in pipes, and that has been one of my interests ever since. As I was doing my master's, I was the second year of my master's, I wasn't quite finished. The chairman of the department called me one day and said, we have a need for a faculty member to teach some courses. We know you've never done this before, and you haven't even finished your master's, but we think you can teach these courses. So they appointed me as an instructor in petroleum engineering, and I taught some courses. I loved working with students. Again, I was not sure if I want to be in the academics or work for industry, and so I decided to go back to Pakistan and work again. But then this teaching bug kept coming back up, and so after about another year and a half of working in Karachi, so I applied and got a fellowship at Rice University. I decided to switch to chemical engineering at that time because I had taken virtually all the courses I could take in petroleum engineering. I came to Rice in Houston and did a PhD in chemical engineering. Just as I was finishing my PhD, I got a letter from the University of Calgary that they would like to offer me a teaching job. So I accepted that. In 1965, I started teaching at the University of Calgary, and it was just starting to build a engineering program in Calgary. So it was very exciting to build something from scratch, design all the courses and teach all the courses and so on. So I was in Calgary till 1982, 17 years. Then 1982, Stanford approached me and asked me if I would like to teach there, and I ended up at Stanford in the petroleum engineering department, and have been there for 32 years and have done a lot of exciting things. In the early 60s, and when I was doing my master's, and later when I was at the University of Calgary, there were no really systematic design methods for multi-phase pipeline. And at the same time, oil companies were moving more and more into offshore areas where it's very difficult to separate the oil and gas and water downhole. So you have a gathering system that has all three phases flowing together. So since I had done my master's in this area, I had a reasonable background in it, and I had kept up with the literature. The big question in designing single phase or multi-phase pipeline is that knowing the difference in pressure at the two ends, how much fluid would flow through the pipeline. So in single phase, it's relatively simple because you're only dealing with a single phase, and theory is well established, and you can accurately calculate how much fluid would flow through. Or if you specify how much fluid you want to flow through a pipeline, and you know the pressure at one end, you want to be able to predict the pressure at the other end for the given flow rate. But for multi-phase flow, the problem is orders of magnitude more difficult because the theory is not well established. And multi-phase flow techniques rely significantly on experimental data, empirical correlations, and so on. So in Calgary, when I was there, we built a very nice experimental system in our laboratory, a pipe about 100 feet long that could be tilted at different angles, and we could flow multi-phase flow through it, make measurements, and then use this information to develop predictive techniques that we could then implement in software. And so the big challenge is really knowing how to predict pressure drop for a given flow rate, or if you have the pressure drop in the pipeline, how much of each phase would flow through the pipeline. What happens is that when the pipe is tilted at an angle, heavier phase like water would flow slower, and the gas, because it's lighter, goes up faster, and the intermediate density phase, which is oil, would be in between the two. So this is called the slip phenomenon. Fluids are slipping past each other, and this is a very important consideration in multi-phase pipelines. And we had to deal with this problem through a lot of techniques that we developed, and we adapted a lot of techniques that other people had developed. So with this background, I thought that would be useful to somehow make these design techniques that we have been working on available to industry on a wider scale. And this was also the time that computers were being used extensively, or more and more, in the industry. So a colleague of mine, Gary Gregory, and I got together and we started writing software, and we had some consulting opportunities to do actual designs for some of the oil companies, and we developed this software and established this company. And it was probably, I'm not positive, probably the first company that provided multi-phase flow pipeline design software to the industry, and it was widely, our software was widely used in Canada and the US, overseas, and different North Sea and so on. And so I think it made a significant impact. And this became especially important in the offshore fields and in the North Slope of Alaska, for example, where you have to design systems for multi-phase pipeline, and this kind of technology had I believe a big impact. So when I came to Calgary in 1965, I had this background in solving equations that describe flow numerically on computers, and so I was looking around to see what kind of problems would be interesting for industry in Calgary that I could work on and use my background in fluid mechanics and numerical solution and so on. So I thought, well, we'd maybe work on modeling flow in petroleum reservoirs, which is really the start of computer modeling, which is now a very big business. In 1977, I started this company, Computer Modeling Group. Initially, it was a not-for-profit corporation supported by the province of Alberta. We did some basic research on computer modeling, and also with a special focus on heavy oil or very thick oils that Alberta has abundance of. Tar sands and heavy oils. So these oils require thermal recovery techniques. Heavy oils have to be heated somehow to make them flow. So we worked in these areas and developed some software for computer modeling of petroleum reservoirs. Some years ago, we saw the need to be able to more accurately predict how long horizontal wells behave. Because see, again, going back to the multi-phase flow problem, in these horizontal wells, you have multiple phases flowing. So this, because these days industry can drill very long horizontal wells, this problem became very important to be able to predict, again, the pressure gradients and flow rates in these long horizontal wells. And so we did a project with Schlumberger, where they made available their laboratory facilities in Cambridge, UK, along with people who were experts in doing these experiments. For about a year or so, we collaborated on these experiments, and we took all this massive amount of data that we had collected. We developed new tools, techniques, for multi-phase flow in long horizontal wells, then that we published. And of course, Schlumberger, because they had sponsored all this work, had first knowledge about these. They implemented these techniques in their software, and it's available now through their software, and other companies have also implemented it. So this is the way I have been working in collaboration with industry, looking at problems that are important to industry, and then freely making available the results of our research to the industry. I think the computers, availability of computers, and the availability of engineers to make use of computer technology through the kind of things I've talked about, I think has had the biggest impact. When I started out as an engineer, we did all of our calculations on slide rules. I don't think most of the young engineers these days know what a slide rule is. And then these little hand calculators, little calculators with scientific functions and so on became available in the 80s. I remember getting the first HP calculator, and I think I paid $700-800 for it. And this is a little calculator, and we thought we died and gone to heaven. What, this calculator could do what we were doing with the slide rule and more, and so much faster. And then slowly computers became more and more common and available. And we started solving problems on computers. And now we have the ability to economically use thousands of processors, very powerful computer processors, to solve our problems, and in a very efficient way and very quickly. And that's why it's becoming possible to optimize, use optimization techniques to optimize controls on wells and so on. So I think all of this is only possible because we have the computational capacity to solve these complex equations. So that, I would say, has had the biggest impact. And along with that, of course, you have to have techniques that can solve these equations, special numerical techniques that are suitable for computers. Computers had a tremendous impact, and I don't think we're done yet. The cost of computing is going down. Our ability to make use of this technology is going up constantly. So through the use of computer technology, numerical techniques, and optimization, there is a huge gain possible. I think there are certainly a lot of challenges, and the interesting thing is that as you overcome one challenge, it opens up new challenges. For example, being able to drill in deep water, then it opens up challenges on how to do this very safely, how to do this in a environmentally friendly manner, and so on. So I think that to me is the biggest challenge, to produce oil and gas from deep offshore fields in a economical, environmentally friendly fashion. And the industry is, of course, realizes that, and there is a lot of emphasis on that, and but a lot more can be done. The impact on the environment has to be minimized. And in the old days, in the 1850s and 60s, when oil was produced, there were these operators who were dumping oil in water streams and so on, but we couldn't possibly think that was the right thing to do now, and we want to be able to minimize. And as we move into areas like North Slope, it's already producing in North Slope, but other areas, offshore Alaska, for example, the problem gets more and more complex. So the environmental concerns get more and more serious, and we have to pay more and more attention to that. That's the biggest challenge, is to produce oil and gas in an economical and fashion with minimal impact on the environment, and we have to constantly work on that. And along with this challenge of not leaving more oil behind than we produce. How do we get? And this is changing. Some of the companies, by applying some of the kind of technologies we talked about, are now able to get 60-70% of the oil out. But it's happening slowly, and as these tools become more affordable for even smaller operators and so on, engineers become smarter and smarter, they'll be able to apply these things and produce far more than we are producing now from a given reservoir. I have worked a bit on in the industry, and but more in academia. But always I have had a very good link with the industry. I've always been interested in solving problems that are important for the industry, and that is because I find this more exciting as an engineer to work on problems that would have an impact rather than problems that may or may not have an impact. So I've worked always in collaboration with industry. I've worked on problems that I thought were important for industry. And as a result, I have had extremely good support from industry throughout my academic career. From the day I started working as a professor to this day, industry has been very supportive of my research. So this kind of work has really been very exciting for me, and if it wasn't exciting, I would have quit by now and done something different. But I continue to work on these problems, and I enjoy very much interacting with the young people on the one side and interacting with people in industry who are working on similar problems and have similar interests. I've had the good fortune to work with some really bright students, lots of them. Many of them have become good friends. I think an ideal arrangement between a faculty member and a student is where we're both learning from each other, not that one is giving and other is soaking up. So I've had students who have taught me more than I have taught them. So that's really the excitement of academic life, and in addition to contributing to technology, that's the most exciting part. This really defines our life, really. What we do, other than family life. This is our professional life, and it's this kind of interaction with industry, and especially through the Society of Petroleum Engineers, has been key to my profession and how I have lived my life. And I've been a member of SPE now for 55 years, I think. That's a long time. And I've seen, I think the first SPE meeting I went to, there were about, I think 500 people, 400 people in Dallas. Now I think, I don't know how many we have here, probably 10,000 or more. So SPE has changed a lot, but I still have friends who were at these meetings long time ago, and they still come to these meetings. So it's so professional organizations, contacts with industry, contacts with students who bring new ideas and have new energies. This all kind of defines my life. Yeah.